Okay, so hello everyone. Today, Sooyeong is going to talk about Kemeny's constant for random walks on graphs.
Thanks, Maria. Hello, everyone. Today I'm going to talk about Kemeny's constant for random walks on graphs. So many of you might not have heard of this object. So I'm going to talk about what that is first. So for that, we have to consider random walks. So random walker is traveling around on the graph. For instance, here when they are in this vertex, for instance, then this person has to move to some place where it's adjacent to 2. So in this case, the probability is defined as the reciprocal of the degree of vertex 2. So it's going to be 1/3, 1/3, 1/3. So for this step, this random walker moves to 1 or 4 or 3 with this probability. After that, this random walker will forget about what happened before. So for instance, where that person goes to here, then he forgot everything, what happened before. So that's called Markov property. And then after that, in a similar way, this random walker is moving around. So we are interested in some quantities regarding this dynamic. So actually, random walk is a special family of Markov chains. So we are focusing on the special family in this talk. So here, first of all, let me introduce some quantity, which is called mean first passage time, or it's called heating time also. So mean first passage time from vertex I to j is the expected number of time steps elapsed before the random walker, which is vertex j, when it begins at vertex I. So for instance, here we consider this graph, and then the matrix below is about mean first passage time. So Mij corresponds to the entries in the matrix here. So for instance, where the random walker starting from 1, then there's only one single path to get to 2. So by only one step, this person can get to 2. So that's why here, this number is 1, m to 1. And then after that, they have choices like 1 or 4 or 3. So instead of directly going to 1, they might be wandering around here, 4 and 3. After that, they can get to 1. So that's why it's not symmetric over here. The number is 7 in this case. I'm not going over the how to find this mean first passage times, but the thing is, using Markov properties, we can get some recurrence relations, Mij, so that we can get some linear equations. Using those things, we can obtain this mean first passage times. So the point is here, by using this quantity, we can define Kemeny's constant. So when you have a graph, and then you can think about the random walk on it. And then here, this quantity, when you take a look at this quantity closely, then this, for any choice of vertex I, this right-hand side is constant. So which means this right-hand side is independent of the choice of I. That's why it's called constant. And then this person found this constant. That's why it's called Kemeny's constant. And here, when you take a look at this part, dj over 2m. 2m is the sum of all degrees, which means we may consider it as the probability of choosing vertex j according to the degree. So this can be interpreted as the expected number of time of random walker to arrive at randomly chosen vertex. So, and then it can be recast as follows, like this. Then here, left part and right part, similarly, we can interpret it as probability, choosing I and j. So choosing I as a initial vertex and then j as terminal vertex. So here, this quantity is the expected time of random walker to travel between 2 randomly chosen vertices, I and j. So this quantity can be interpreted as the expected length of a random trip. So here, when you have Kemeny's constant, smaller Kemeny's constant, which means when you pick 2 random vertices and then And then that time, travel time is shorter, which means we may consider it as our graph is sort of connected, well connected. If it's not, then travel time would be longer. So that's why Kemeny's constant can be considered as measuring how well connected the graph is. So this is a graph invariant. We have a graph, then we can get this Kemeny's constant uniquely. So this graph, when you're given by some graph invariant, then you might be wondering about how the graph structure affects your graph invariant, right? How should it look like? Something like this. So we may have natural question like this. How does graph structure affect Kemeny's constant? So to increase connectivity in terms of Kemeny's constant, how does graph look like? Like maybe should it be sparse or dense, sparsity, or when you pick two vertices at random and then are they far away each other, then does Kemeny's constant is larger, or so distance between vertices. So maybe you can think about various factors that affect Kemeny's constant. So this is what I'm gonna do today. And then for that, let me introduce some ingredients. Before that, let me introduce some examples. Let's consider those families: star, path, cycle, complete graph. Then star, as you see here, n minus 3/2. We are gonna go over how to find those things. And then here, path. This has the largest diameter. Obviously, this is greater than this. And then when you think about cycle, then it's also about n squared. Right? Its diameter is growing, right? And then this complete graph is diameter 1. And then n minus 2 plus n over 1/n. Then when you see this, then you can see that this Kemeny's constant is less than this. And so on. So yeah, maybe some diameter is affecting or some sparsity. This is really pretty dense graph, right? Okay. So for that, let me introduce some various formulas. Instead of using definition, we can use other formulas. So Kemeny's constant can be expressed in terms of the spectrum of the transition matrix here. D is the degree matrix, and then A is the adjacency matrix of graph G. Then here, this D inverse plays a role like normalizing each row of A, which means when you take each row, then when you take sum over all entries, then you have 1, which means all one's vector is going to be your eigenvector corresponding to eigenvalue 1. And then lambda 2 and lambda n various eigenvalues. And then in Markov chain theory, this second largest eigenvalue, lambda 2, this is some non-increasing order. So in Markov chain theory, lambda 2 plays an important role. It has to do with so-called mixing time, which means when you have initial state, then it converges to some stationary vector. So it measures how fast it converges and so on. And then this also related to Cheeger's constant. And then, so you might be wondering, why can't we use those things? I mean, for instance, Cheeger constant. But when you take a look at this, then Kemeny's constant has to do with other eigenvalues. When you have large enough n, then you cannot actually ignore the other eigenvalues. So that's why that there's some discrepancy, difference for using mixing second largest eigenvalue only, or we have to use the other eigenvalues. And here we have some note. Since we are using eigenvalues, if our graph is regular, then D inverse becomes the scalar multiple of identity, so that these eigenvalues can be obtained from adjacency eigenvalues, like multiplication of 1/r. So that's how we can easily obtain Kemeny's constant for cycle and complete graph. And then there's another formula. This is in combinatorial setting. So here, this formula is really good because this formula makes a sort of bridge between, Kemeny's constant and Markov chain theory to enumerative combinatorics. So when you take a look at this matrix, Fij, which is an entry of matrix, this is the number of spanning two for each. So one contains vertex I, and then the other contains J. So this forest actually separates vertex I and J, right? And then this Kemeny's constant can be expressed in this way. So M here, the number of edges, tau is the number of spanning trees, and then D is the degree vector. So let me give you an example. So we have four vertices graph, and then since this is a unicyclic graph, so it has cycle of length 3. That's why we have three spanning trees. And then here we have to set, in order to find this guy, we have to separate two vertices, 1 and 4. So you want to cut this part to separate this. Then we have this isolate vertex and then this 3 cycle. So we have 3 options, right? Here, we can generate 3 subtree like this, right? So this is 2 forests, and then it spans all the vertices. And then this part, when you contain these two and then cut these 2 edges, we obtain this. And then here containing this part and the isolating vertex 1, we have this spanning 2 forests. So there are five spanning forests. When you do this job, you can get the Kemeny's constant by using this formula. And then here, there's a note. When our graph G is 3, then this matrix F becomes the distance matrix. So that's how we can easily obtain this in the example of star and path. Because we can get easily the distance matrix, and then you can use this formula, and then tau is going to be 1, and then m is n-1, and so on. So let me introduce the last formula. Of course, there are more formulas, but these formulas are what I'm going to use today. So R, the matrix R, is defined as the matrix whose entries Rij is the effective resistance distance, which comes from electrical network. So between vertices I and J, and then it is known that this quantity, this distance, resistance distance, is related to the number of spanning trees via the number of spanning trees. So by using the previous formula, we have this another formula. The reason why I'm producing this is it has to do with Markov index. This is another graph invariant, which is well known and then well studied. And then this is a graph invariant, and then it's defined as here half of the sum of all entries of R. So we make a connection between Kemeny's constant and Markov index under the condition that G is regular, like this. So we are using Markov index later. So yeah, this is all ingredients that I'm going to use today. So today's topic is going to be, I told you before, but let me repeat this. So Kemeny's constant is a graph invariant, and they can be regarded as a measure of graph connectivity. And then we are interested in how the graph structure informs a graph invariant. So here we are going to study it via asymptotic behavior. So considering asymptotic behavior gives us some good intuition, right? Rather than focusing micro things. So for that, let me introduce some notation. So we are going to consider Gn, which is a sequence or family of graphs. N represents the number of vertices. Then we are going to use big O notation and big omega notation and big theta notation. So simply speaking, here big O notation means when you have a function f, then if it's bounded above y, your function g, then of course large enough n, then this is big O notation. And then your f is bounded below by function g, then this is big omega notation for asymptotically. So your function f is between constant times of g, constant times of g. It's between these two things, then we are using big theta notation. So let me give you an example again. We have a star and then we found Kemeny's constant like this, and then obviously this is big theta of 1, n, and then n squared, n, like this, because we find an explicit expression for this. And then here, it's proved that the Kemeny's constant for complete graph is the minimum. So for any graph is greater than equal to Kemeny's constant of complete graph. This means Kemeny's constant of any graph is big omega of n, right? Any questions or, okay. So I raised some two factors, sparsity and diameter. So let's think about this. And then we have proved this result, which is it's simply proved by using Markov index. So resistance distance. Here, from this inequality, what we can say is, if you want to attain larger Kemeny's constant, then your graph necessarily have many edges, the number of edges, and then the graph has some larger diameter, right? Necessarily. So for the proof, we are going to use the definition here. And then here, it is known that here Mij and Mji is 2n times resistance distance. So vertex I, vertex j. So mean first pass time from I to j, and then j to I. So we are summing them. So this is called a commute time. So this quantity is equal to 2 times the number of edges and then resistance distance. By using this, we obtain this inequality. And then here for this part, this resistance distance is always bounded above by diameter of g. That's how we've got this inequality. And then from this, we have some note, which is m is bounded above by n squared, and then diameter bounded above by n. So any Kemeny's constant of any graph is bounded above by n cubed. And then if your graph has fixed diameter, then here this part is constant, then maximum order is gonna be n squared. So you might be wondering if this upper bound is sharp. In other words, can you find any family of graph whose Kemeny's constant is of order n cubed? We have seen families, right? Path and cycle. Those two families are of order n squared. Can you find such a thing? Then the answer is yes. And then here, so this type of graph is called a barbell graph. So this part is it looks finite, but I meant this is clique, like size is n third. This part is n third, and then this part is n third like this. So when n goes infinity, then diameter is increasing, growing in n, right? And then the number of edges is of order n squared as well. So, and then explicit Kemeny's constant is given by this in this paper. And then it turns out that its order is n squared. Then we are wondering what other fact, other than sparsity and diameter, what kind of other factor influences on Kemeny's constant. So maximum degree could be a candidate, because when you think about graph, and then if you have a vertex here with a maximum degree, and then the other part is here, if you have larger maximum degrees, which means it's adjacent to most of vertices in your graph, then in here, when you pick two vertices at random, say they are likely to lie on here, right? And then when you think about mean first pass times, then from here to get to the other, it could be get to the other via this, like this, throughout the maximum degree. Suppose that if it's not passing through the maximum part, then it goes here, but this vertex still likely to be inside of the neighbor of the maximum degree, vertex with the maximum degree. And then this vertex has a route to get to here, and so on. So we might expect that if we have a larger maximum degree, then our Kemeny's constant is going to be lower. Maybe this would be a reasonable speculation. Indeed, it works. Like we have a connected graph G, and then our maximum degree is n minus big O of 1. Then Kemeny's constant is big theta of n. And then more concrete result, when we have a Kemeny's graph with a maximum degree n minus 1, then Kemeny's constant is bounded above by 2 times n minus 1. So I'm gonna show you a sketchable proof for this theorem. Using similar idea, we can prove this, but this is a bit requires more things. So that's why I chose to show some proof of this. So let me introduce some sketchable proof for this theorem. So here, let's choose I as a vertex with a maximum degree, which is n minus 1. Then we have seen this relation, resistance, distance, and the number of spanning two forces. And then we have seen this, right? To find the upper bound, 2 times n times diameter of G. Then here, this part can be written like this. So let's focus on this expression. Then here, I claim that dj times fij is less than or equal to 2 tau. If so, right-hand side becomes summation of 2, which is going to be 2 times n minus 1, right? So to prove this inequality, I'm going to convert this question into enumerative combinatorial questions, which is here, left-hand side represents combinatorial object. I'm gonna choose some combinatorial object that represents left-hand side, and then I'm gonna choose some other combinatorial object that represents right-hand side. So for that, here, let me define the notation as n of j is the neighbor of j. And then here, I'm gonna use this notation f sub v, I, and j as the set of spanning rooted two forces separating I and j by labeling v as root. So which means you have a forest, two spanning forests. One contains I, the other contains j, and then there must be some vertex v here or here. But if it's here, we are gonna assign this vertex as a root. So that's all. That's what notation means. So when you have different v's, then they must be a disjoint union, right? Because when you have different vertices, then they are different roots. So this union is obviously it's a disjoint union. So cardinality becomes dj times f sub ij, because v is in the neighbor of j. And then so this combinatorial object represents the left-hand side, and then right-hand side. Similarly, we are gonna pick all possible spanning trees, and then we are gonna assign I as a root, which is denoted by ti. And then root, if you assign your root as j, then it's gonna be tj. So obviously they are disjoint union, and then cardinality is 2 tau. So the remaining thing we have to do is we have to find the injection map between these two combinatorial objects. So this is the map. So here, so we have two spanning two forces like this. So I is here, and then j is here. So in this case, because our spanning two forces separates I and j. In other words, your vertex v must be either adjacent to I or j, not both. If it's adjacent to both, then it's not gonna be spanning force. I mean, not separating I and j. So this is well defined in the sense that this v must be adjacent to I oh, sorry, not adjacent, connected to, sorry about that, connected to I. And then, so in your spanning forest, and then V is connected to J, but not to I. So we can divide two cases. And then if this case, we are gonna send this forest to this spanning tree by adding this edge here, and then replacing the root by J, deleting root V, and then we are assigned J as root. Similarly here, like adding edge here, generating a spanning tree, and then assigning I as root. So this may be, you can verify that this map is well defined, and then you can also prove that this is injective. So by proving that, we can prove this inequality. Oh, sorry about that. Here, we can prove this inequality. Therefore, we have this upper bound. Similar idea is applied to here, so we can prove this upper bound as well. So we have seen that if we have a maximum degree, as the maximum degree large enough, then at some point Kemeny's constant is going to be of order n. So now we are going to consider graph and the complement of graph together, because this is also natural question. Like you have a chromatic number, and then you're considering a graph and a chromatic number, and then it's natural to think about the chromatic number of complement of graph, right? So that you're thinking about the sum of chromatic numbers and then the product of chromatic numbers. That's called a Nordau-Scaling problem. So we are gonna consider, instead of chromatic number, we are gonna consider Kemeny's constant here. So you have a graph invariant F, and then the Nordau-Scaling type problem is to find lower and upper bound for the sum of your two invariants for G and G bar, and the product of two invariants. So here we are going to consider Kemeny's constant for F. So this provides insights into the interplay between a graph and its complement. So we want to see if one of two Kemeny's constants is going to get larger and larger, what's going to happen the other. That's what we want to see. So for that, before we dive into some result, let's think about some observations from what we have done. So maximum order of Kemeny's constant is n cubed, right? So the sum of two Kemeny's constants, of course here, I assume that G bar and G both are connected because Kemeny's constant is defined for connected graphs. So this is the underlying assumption when it comes to Nordau-Scaling problem. So the sum of two Kemeny's constant is maximum order is n cubed. So this would not be that interesting, right? It's obvious upper bound, and then we can find a family of Kemeny's constant attaining this maximum upper bound, which is on barbell type graph. So what about product? Product is going to be maximum upper bound is n to the power of 6, but we can make it sharper by using what we have seen. So here, it is known that this is a well-known fact. If we have a graph G whose diameter is greater than 3, then the complement of that diameter is going to be 2. So we have seen that if we have a fixed diameter, then maximum order of Kemeny's constant was squared, right? So if you have a graph whose diameter is greater than 3, then automatically Kemeny's constant of G bar is going to be n squared. And then this part is maximum order is n cubed. So we have this upper bound. And then if your graph diameter 3, then G bar is going to be 2 or 3. Both are fixed diameter. So maximum order is n to the power of 4. So the question is this upper bound is sharp? So we don't know yet. We haven't proved, or we have verified some family. We haven't yet. So we don't know yet if it's sharp or not. Okay, so let's consider barbell graph again. So you might be wondering if this guy is gonna be the family attaining the upper bound, n to the power of 5. So when you think about this, then this vertex degree is n minus 3. Then here, maximum degree is n minus 3, which means n minus big O of 1, right? We have seen that each Kemeny is constant bounded by constant times n. So it follows that the product is going to be n to the power of 4. So this is not what we want, actually. Okay, so let me introduce some result regarding maximum degree. So in this result, we have some real constant, which is between 0 and 1. And then this proposition, this theorem says that if maximum degree is bounded above by constant times n, then one of two Kemeny constants here is going to be bounded above by some constant times n. So this is quite strong. And then the proof of this is 7 pages long. So I'm not going to go over the details. So let me give you some just brief idea about this theorem. To understand the idea, we need to understand Chigger's constant. In other words, Bottleneck ratio. So let me introduce that concept. So we have seen that Kemeny's constant is expressed as this. And then we are going to focus on second largest eigenvalue. So this is obvious, trivial, lower and upper bound from here. And then to define Chigger's constant or Bottleneck ratio, we are going to consider this notation. So any subset of vertex set S, here volume of S is defined as the sum of all possible degrees. And then we are going to define this notation as well. So when you have two disjoint subsets in your vertex set, then this bracket of S and B means the set of all edges. So here S and T and these edges between S and T, we are gonna collect those things and then we denote it by this notation. And then for that, I'm gonna define this ratio. So bottleneck ratio, which is defined as phi, which is minimum under this constraint and this over this. So for this ratio, it is known that this is in Markov chain theory. It is well known. So second largest eigenvalue is bounded below and above by this. So we have this expression. Then what we are gonna do here, so the directional proof is we suppose that Kemeny's constant is sort of large. Then when it gets large, then this phi should be lower, right? So this phi is lower means there must be some set S such that this denominator or numerator, so this is large or this numerator is lower, right? So this gives us information about G. And then let me show you this picture. So we have larger Kemeny's constant, then phi is lower, then our graph G should be of this form. But not many edges between S and S complement here. And then when you take complement, then we have many edges between there. And then we can get further information. So actually I haven't really specified the condition of this, which is the maximum degree about this, right? So from this condition, we can obtain further information like this. So in your set S and S complement, then you can choose, you can pick set A and B, satisfying this condition. Every vertex in set A is connected to most of S complement. So when you pick vertex here, then connected to most of S complement. Vice versa here. Here, pick vertex, then most of vertices here. And then further, S minus A, set difference. S complement minus B, this is relatively smaller than this size of A. So this structure forces mean first pass time. Oh, sorry about that typo. Mean first pass time between any two vertices is gonna be of order n. So what that means is here, dj and 2m, mij. So this is gonna be order n. Then this part is gonna be big O of 1. So this implies that Kemeny's constant of this complement is gonna be of order n. This is the big picture of the theorem. And the details of these things requires a lot of job. And then, okay, so here we have seen this theorem, right? And the maximum degree actually really something to determine Kemeny's constant, even Nordau's theorem problem. So for this, we can get this corollary. So when you have a graph G, and then if you think about complement and then your graph G, both are regular, and then one of them must satisfy this condition, right? Therefore, one of two Kemeny's constants must be bounded above by this. So let me note about this. So far, we have proved this in terms of maximum degree. So n minus omega of n, or n minus big O of 1, then we have Kemeny's constant like this. Nordau's theorem problem. The product of this is bounded above by this. Then here, what other maximum degrees then? For instance, n minus root n or something. So we don't know what's gonna happen here yet. So, okay. And here, now let me introduce some various families to get you have some sense of how graph structures affect Kemeny's constant. So let's consider regular graphs for Nordau's theorem problem. Then we have seen this relation, Markov index and Kemeny's constant. They are related under the condition that G is regular. Then here, in the result, from the results in Markov index, we have this. And then applying this formula inequality to here, we have this lower and upper bound for regular graph. Of course, for your information, so this upper bound is not sharp. We don't know yet. It has not been proved about sharpness about this upper bound. And here, so this implies that Kemeny's constant is bounded above by n squared for regular graph. And then here, by using the theorem, we have proved corollary. So one of these two Kemeny's constant must be big O of n. That implies that when you have Kemeny regular graph G, then the product of G and bar is always bounded above by n cubed. And then let me provide another family. So here, so I generalized the Barber type graph. So instead of considering here this part as click and click, so I consider arbitrary graph G1 and G2. Then using some formula for graphs with bridges, then we can find this lower bound, which is about the number of edges of G1 and G2. And then here, D is the length of this, the number of vertices on this path. So here, if D is of order n, and then both the number of edges, G1 and G2, are of order n squared, then we have this order. So in other words, not necessarily this part, G1 and G2 are not necessarily click. So if they are enough dense enough, then we can attain Kemeny's constant of order n squared, n cubed. So for instance, if you pick G1 and G2 here, this as a complete bipartite graph, then the number of edges is still of order n squared. Then you can arrange properly. Then you can make the entire graph as bipartite graph. So for instance, we can show that there exists some bipartite graph whose Kemeny constant is of order n cubed. And then as we have seen that here, this part, the degree of this in the complement is n minus 3. That implies that the product is of order n to the power of 4. So to increase your Kemeny constant from this, we can understand that to increase our Kemeny constant, maybe it'll be better to make bottleneck phenomena here, as we have two bottlenecks both sides. That's why our Kemeny is constantly getting higher. And let's think about tree. So tree. So there's some interesting result about Kemeny constant is related to another graph invariant, which is called a winner index. This is the sum of distances for all pairs of two distinct vertices. So this definition is not necessarily for tree, actually, for generally in graph. But when it comes to tree, so Kemeny constant is related to this. Then as you see here, the sum of distances, to make it larger, then maybe you might have to increase the diameter of graph tree, right? When your tree has larger diameter, then distances for some pairs are gonna get increased, right? That results in a larger winner index. Indeed, the maximum winner index is obtained by path, and then the smallest winner index among trees is obtained by star. So here the maximum order is going to be n to the power of n cube, and then here there's n is in denominator, so we have Kemeny constant as n squared, and then every tree has a pendant vertex. That implies that the complement of tree is going to be order n. So that's why we have this product, the order of product. So any questions? Okay, so let me introduce the last family for Nordhaus-Galerpi problem. Then here, so I'm not going to go over the details or for the definition. So here, let me just briefly introduce the results about distance regular graphs. So we have seen that diameter 1 case, complete graph, right? It's order n. And then diameter 2 case, it's going to be strongly regular graph. Then using the formula in terms of spectrum, so we can find that its Kemeny constant bounded above by n. So, and then also we know that the complement of strongly regular graph is also strongly regular graph. That implies that we have this. And then instead of considering Nordhaus-Galerpi problem, I was interested in this. So recall that our cycle is of order n squared, right? Diameter is growing. So in regular graph, does diameter really affect the order of Kemeny constant? So what if we have some distance regular graphs with growing diameter? Then their Kemeny constant is going to be order n squared or n. So the answer was no. So for instance, the spectrum of distance regular graph with classical parameter is found in this paper. Then using those formula, we can verify that some families of distance regular graphs with classical parameters, for instance, Hamming graph. So more specifically, like you can think about hypercube. Then hypercube in that case, the number of vertices is 2 to the n, but diameter is log of n. So yeah, diameter is growing, but it's very slowly growing. So Kemeny constant is big O of n. And then we can also verify that other families, here in this book, in these families, their Kemeny constant is of order n, while their diameter grows as n increases. Maria, I should I have a 3 minutes. Is that right? Sorry. Okay, 3 minutes, right? five. Okay, let me briefly tell you about the results about this. So instead, what we have seen is sort of macro viewpoint, right? Like considering asymptotic behavior, and then we are thinking about the order. Instead of that, we can think about what if we add an edge, into a graph, and then how does Kemeny's constant behave? Like our intuition would be when we add an edge, then maybe we might expect that Kemeny's constant increases, right? That's gonna be really well-connected graph in some sense, but it's not. So does Kemeny's constant decrease after adding a new edge? So this is a question, and then here we have seen some relation between Kemeny's constant and Markov index, right? In Markov index side, it is known that addition of a new edge always decreases Markov index. But for Kemeny's constant, it does not hold for Kemeny's constant in general. So such an edge, when you add an edge and then that graph, Kemeny's constant get increased, then such an edge is called a brace edge. So for instance, here, you have a graph G here, adding an edge. Yeah, instead of decreasing, we have larger Kemeny's constant. So this guy is called a brace edge. And then here, so let me show you another example. So we have this graph here. I'm gonna fix this part, right? And then I'm gonna increase this the length of cycle, like 4, 5, 6, and so on. And then the number here means the difference of Kemeny's constant after adding edge and before adding edge. So if it's positive, that means Kemeny's constant increases. So in this case, you can see that the diameter of this cycle getting increased, then your Kemeny's constant, the difference is getting increased, right? So I was wondering if it's all about diameter about this graph. That's why I investigated this topic. So we have a tree here, and then we have a bunch of path here. And then, so I want to see if this guy becomes a brace edge or what. So this was my question. So T, in this case, T. So I have verified that. So let me simply speaking about this. So if we have an eccentricity of this vertex V is getting larger and larger, then this is gonna be a brace edge. So the eccentricity, so the farthest distance from V is getting longer and longer, then this becomes a brace edge. So let me give you an example here. Well, not example actually. So when you think about path, then there's a center vertex. So if I create a cycle by adding this edge, then you can see this part. The length of this is shorter, quite shorter. So that's why it's not a brace edge. But when I shifted this cycle, passing by center and then toward this endpoint, then this cycle, it's not likely to brace edge, but when I shift it towards endpoint, then it becomes a brace edge. So this phenomena happens in path. And then this fits into this result. I mean, intuition of this result, actually. So, and then you might be wondering how many brace edges in this path, right? So all possible non-edges is n choose 2, right? This is Pn, then n choose 2, n choose 2 minus n minus 1. This is all possible non-edges for this path, right? And then we counted how many edges for brace edges. Then the result was this. The order is n times log of n. Still, we can see that the number of non-brace edges is dominating over this, right? So I think I should stop here, and then this is the last slide. And then thank you.
Thank you very much. Any questions for Sooyeong? So while I did have one question, So, is there analog of Kemeny's constant for quantum walks? That's
a good question, and then that's a topic that I'm interested in actually recently, and then yeah, the one thing I want to point it out, actually, I had a conversation with Harmony, and then sorry about that. So for instance, here about Kemeny's constant here, we have this quantity mean first passage time, right? And then in this case, we use the Markov property, right? So we have to think about we can ignore what it happened before, and then further. So this Mij can be written as some the first time, for instance. Should I say? So zero step, first step, second step, third step, and so on, right? Then Mij can be split into the sum of 1 plus summation of mkj. K is not equal to I or something. Sorry. Sorry about that. So what I want to say is here for there's some concept quantum heating time. So for that, that's analogous concept as mean first passage time. The different thing is we cannot apply that thing. So after first step, what I meant is sorry about that. I'm not ready to answer that question. Anyway, there's a difference between those things. So that's what makes it difficult to develop Kemeny's constant in here. And then, so yeah, I didn't expect that question. Sorry about that.
No, I'm asking because I'm interested in quantum things, and then I thought maybe you know. So whatever you said.
I am working on this, and then once I have a clearer answer, I will let you know. Yeah.
Okay. Yeah, that's interesting.
I have a follow up to that. Because the Mij, right, is the first that's the time at which the state in I reaches J. But in quantum walks, I'm not sure what that would mean. Like there's PST between I and J, but that doesn't really happen.
But when I was thinking about the quantum walks in the analogy, when we measure the probability of how much the walks around, right? So there's stationary property of a walk if you consider average mixing matrix, right?
Oh, okay.
So yeah, so that's what I was thinking, but I don't know much about it. So
another thing is there's no stationary vector in quantum walks.
Right.
I think.
Yeah,
so
it doesn't converge.
Another thing, because this part has to do with a stationary vector, so that makes another difference. So I think there's some question from Martin.
Yeah, I want to add to this comment that, I mean, you can define these hitting times and so on by including the measurement. Essentially, that's the vertex to which you hit. You have to include the measurement, so you project out the amplitude that lands on this vertex. And the thing is that you can have quantum walks which have infinite hitting times, like that you have a finite graph. And say if you have the coin, if you have this discrete time quantum walk with the coin, you have, for example, the Grover matrix typically leads to that. But when you have cycles in the graph and you start from a vertex which is in a cycle, then I think you typically will have infinite hitting times to other vertices.
I see.
The probability to ever reach that whatever vertex will be strictly less than 1. Well, it also might depend on your initial state and so on. So there might be a lot of these complications. But I think it's very interesting topic for in the context of the quantum walks. Thanks. Really nice talk.
Thank you for your comment, I think.